Okay, so again, I, I'm totally sympathetic. I know how hard it can be to just kind of talk for hours and hours and hours on end. And so I'd like to help Connor out by kind of just being able to break up some of the things, and maybe it could end up actually helping some students out by kind of splitting things up to maybe like 2 hours on Tuesday, 2 hours on Monday, 2 hours on Thursday, 2 hours on Friday or something, rather than having 4 hours in a row on Tuesday and 4 hours in a row on Thursday. So please be on the lookout on CampusWire for some kind of poll to help us kind of figure out how it's going to work best. And we'll kind of go from there. Okay, are there any questions or issues before I get started on, I guess, what I was going to say today?
Professor, I got a question.
Yeah, go for it.
Am I being counted late for this lecture?
Are you what?
Am I counted for late this lecture because I'm
Late?
late, like
Oh,
late?
no, I don't.
Because
So there's no tardiness. Like I'm not like watching the logs or anything. And I have not given any kind of I haven't given any view quiz answers yet. So no worries there. And don't worry, I'm not monitoring who's like checking in like 2 minutes after the clock or something like that. So don't worry about that. And basically, if you join in and you're listening along and you only like by the time I say, okay, and your next view quiz answer is this, and you realize you didn't hear the first one, then you'll just have to go back and watch the recording to kind of catch that first view quiz answer, something like that. That's how it's going to go. Okay. All right. Well, again, thank you guys for being here. And again, if you are willing to turn on your cameras, it is always much appreciated to kind of just see students rather than empty boxes with names. So thank you to those of you who have turned on your cameras. And let me see what I can do here. Okay, so we'll be doing that. There's a question: will we be working in groups for the labs? I was not planning on anybody to work in groups for the labs, but perhaps I'll talk to Connor for his thoughts there. But that was not the plan. I kind of want you guys everybody to experience a little bit of the joys of R. So, all right. Okay, just a couple reminders before everything else. Your first homework assignment is due on Sunday at 6 p.m. And a student had asked me, they have a tablet, an iPad, and they were wondering if they could just do their homework on the iPad. Yeah, totally. You don't, just because I said scan and submit your homework does not mean you actually have to do it on paper, scan it, and submit it, right? Pretty much the homework you're going to be doing by hand. I suppose if someone wanted to go through the trouble of typing out their answers, like, we're not going to take off points for that, but that seems like way too much work to try to type out your answers. So I figured you would just write your answers by hand, and then it would be easy to take a picture and upload it. If you want, you can use an iPad, write out your answers via iPad, save it as a PDF, and upload that. Okay, and again, it's based on completion, not based on correctness. It's up to you to kind of check to make sure you've done your own, that you've done the answers correctly. I've posted some videos. Those videos are super old, but I think the numbers, the values that are in there are still kind of correct. Those are from my like early days of teaching. But yeah, the textbook publisher hasn't really changed the actual problems themselves. They've updated some of the content in the textbook and things like that, done some refinements. But that's what we've got. Okay. Also, this weekend, whatever, Monday, you'll have your first quiz. So this is going to kind of be our weekly schedule. Quiz 1 is released Sunday at noon, and it must be completed by Monday 11:59. So anytime within that 36-hour window, set aside 1 hour to complete your quiz. You'll start it. You do it inside the browser, and it's done on the Gradescope website. Okay, and so you'll see it there. So I will post a link in week 1 of CCLE. I know it's technically the start of week 2, but look for week 1 of CCLE, and you can click that. It'll open up the thing in Gradescope, and you will take your quiz there. Okay, and once you start it, you got 1 hour, and that's that. Okay. The quiz is open note, open book. You can use a calculator. You can use R as a calculator. Really, the only thing you're not allowed to do is to discuss the quiz with other students. That's what we've got. Okay. Most of the questions on the quiz are going to be kind of short answer. There's going to be and kind of similar questions are going to be grouped together. So there will be some kind of prompt, and then you'll kind of type in your answer. So for example, the first few questions of the quiz, I'm going to give you like a set of numbers, maybe like a dozen or so numbers. And I'm going to ask you to say, find the median of these numbers. And you'll say, oh, you know what, the median is 25. And then there will be another question. It says, find Q1 of the quiz, Q1 of these numbers. And then you'll say, oh, okay, Q1 is 18 and Q3 is 29 or something, and you'll just kind of type in those numbers. Okay. And Gradescope is going to kind of just auto grade those things. And so if your numeric answer matches the solution, you'll get credit. Okay. Some of them you have to type in your number exactly, and then other numbers, I'll tell it, to accept any number with plus or minus 0.002 or something like that, where like if you have a rounding error, you can still get credit and things like that. And then, and if it's wrong, or if it's outside of that range, or if it's not the exact number, depending on the case, Gradescope will give you a 0. All right. Now, some of the questions are going to be worth multiple points, and we'll have the kind of the opportunity to earn partial credit. This is entirely optional. And the way it's going to work is, so I imagine as you're taking the quiz, you're going to have to write some things down by hand, right? So some of the things you might be able to look at and just say, okay, the answer is this. But other things like, find the, I don't know, today we'll talk about, find the standard deviation of a random variable or something like that. I imagine you'll have to do some work by hand, and optionally up to you, you can scan your work and upload it. Okay. Now, if you don't want to do that, you don't have to do that. Okay. But if you don't upload your scratch work and you get the wrong answer, you'll get 0 points. Okay. If you don't upload your scratch work and you get the correct answer, you'll get full points. We will not take off points for not uploading your scratch work. But if you get the wrong answer and there's no scratch work, you get 0. If you get the wrong answer and you have scratch work, and we look at the scratch work and it looks mostly good, but you made a small mistake or something, we can give you partial points. Obviously, if your scratch work shows a lack of understanding, we can't give you points for your bad scratch work, but that's a possibility. And this is like the unfortunate thing about online testing and online learning. It's going to be a tiny bit annoying because, there's probably like 5 problems or something, I guess 5 groupings of problems. And each one, it'll be like, upload your work for this problem if you want, upload your work for this problem if you want, and things like that. And that means you got to kind of like scan 5 different files and upload 5 different files. And I know that's annoying and that's tedious and time consuming. And so I've taken that into account as far as the timing of the quiz. I figured the actual quiz itself should take 45 minutes or less. And so I'm giving you guys 60 minutes for this quiz, where you have kind of 15 minutes of additional time to cover the scanning and uploading of the work. Okay. Is there a question? I see a question from Geetika.
Yeah, it's Geetika. I was wondering for the quiz, can we scan, if we have scratchwork on one PDF for all the problems, can we just upload that for every question, or do you want us to do it separate?
That's fine. If as long as it's clearly identified. So yeah, if you do like problem 1 and problem 2 and problem 3 on the same page, you can just scan that one page and upload the same file for problem 1, problem 2, and problem 3. And the grader will see that and they'll know, okay, this is the work for problem 1. This is the, this part is the work for problem 2 and stuff like that. So that's fine. Okay.
Thank you.
So sorry, I also have a question.
Yeah, go ahead.
So as you said, there's like a group questions, like the first group might be short answer and all that. Like do they have to have like separate form like PDFs for the first section and then a separate PDF for the second section?
I mean, no, it's not required. Again, I think that was the other student's question where can you scan like one file and upload it into kind of different sections? And that's fine, as long as your file is kind of clearly labels the work. Okay, so we can kind of do it. So depending on the problem, I don't know how many scratch sheets of paper you'll have, but if you fit everything on one, that's fine. If you have two, then probably you should separate them out and upload the first page for the each page for its relevant problems and stuff like that. Okay, and again, this is optional. This is if you want the possibility of partial credit. And fortunately, on Gradescope, as long as you as long as you've typed in your answers, if like time runs out while you're doing like the scanning of the PDFs and uploading, like it'll just submit your quiz, I think, with all of the answers that you've put in there. Okay, I think there's also an option to just kind of submit what you have, and then you can always kind of, while the window of time is still open, while that 60 minutes is still open, you can kind of go back and modify answers or add insert files and things like that. But ideally, just kind of plan things. Give yourself, I think, a good 10-15 minutes for the scanning and the uploading, if that's something you want to do. All right. Are there any questions there as far as how this is going to work regarding the quizzes? Okay. All right. I'm going to go ahead and assume everyone's okay with that then, and we'll start with the content of the day. All right. So today we're taking a look at chapter 3 in the textbook, and we're discussing probability. Oh, I talked to the bookstore people, and they said everybody, if you're part of inclusive access, you should have access to the content. I don't know if anyone's having trouble accessing the content and they're part of inclusive access. Okay, and again, if you do not want to be billed for access to the textbook, you need to opt out. Basically, do it tonight, or I think tomorrow's the deadline. I don't know exactly what time tomorrow, but I would just say, just to be on the safe side, make sure you do it tonight. And you should have received an email with kind of instructions on how to opt out of inclusive access if that's something you want to opt out of. Where do we access the textbook is the question. So let me pull up the browser. So under the browser, or in on CCLE right here, there should be this section that says UCLA Store Course Material, and you click that, and it takes you to this page over here, and you should see it. You should see it here, and then you click Read Now, and you've got to kind of, you have to read it in your browser. That's how they make sure you're not like gonna sell a book to other people or something. But this is okay. Yeah, this is it. Okay, so today we're doing chapter 3. The table of contents is here, and when you do say chapter 1, you can look at the problems, things like that. Okay. So anyway, it's under on CCLA, there's this section that says UCLA store course materials. Okay, so hopefully the bookstore has resolved the issue and everybody can access it. Okay, and again, if you stay, like if you don't do anything, you will be billed $40-something for the textbook. And if you don't want that to happen, you need to opt out and you need to do it tonight. Okay, someone made a suggestion about learning objectives, and that's probably a good idea. And so this is kind of a quick bullet point list. I don't know if this is like how we do learning objectives, but this is going to be kind of the stuff we're going to cover today. And these are kind of the key ideas here. So, you know, when you go back and you reread these notes and things like that, this is what we're going to cover: definition of probabilities, rules for finding probabilities, conditional probabilities, independent events, random variables, and things related to that. Okay. In chapter 3 of the textbook, the last section is on the binomial random variable. We will cover that in the next lecture. All right. So if we take a step back, we talked a little bit about this in Tuesday's lecture about the role of probability. And basically, as far as statistics goes, what we want to do is we want to make conclusions about the population based on what we see in a sample, right? And an important part of these conclusions is trying to decide if, you know, the data we see in our sample, is it just a result of a random fluke, or does our data actually reflect some kind of phenomenon that's actually happening in the larger population? We're not able to observe the larger population directly. Again, we're looking only at a little sample, and somebody can always argue, you know what you see in your sample is just a weird coincidence, right? What you see in your sample, that's not actually happening there. That's just some weird coincidence. That's a random fluke. And in order to kind of reason about that, we need to understand, well, what is possible under randomness, right? Because technically, anything is possible if it's truly random, but even though anything is possible, many things are highly improbable. And so we want to kind of learn these rules of probability to help us decide what is probable or not probable and things like that. Okay. So I don't know if you guys ever play board games and things like that, but I like board games. And a lot of board games use dice as part of this kind of random mechanic. And so, you know, for example, you might play this game called Settlers of Catan, and you try to roll these things, and if you roll the number 7, there's like a bad guy that will come and steal your stuff, and or you're maybe the person is stealing your stuff, and you're just waiting for someone to roll the 7 to kind of move your character, the robber, off of your property, but and so anyway. You're just waiting for this to happen, and maybe it just doesn't happen for a long time, okay? According to probability, if you roll 2 dice, okay, one, you know, 6-sided dice, 1 through 6, there's 36 possible combinations, there's 6 possible ways to roll a 7, so we should roll the number 7 1/6 of the time. And maybe you keep track of all of the dice rolls, and you know, that you're a little obsessive about this. And maybe after a full game, maybe you said, we rolled the dice 72 times, and out of the 72 times, we rolled the number 7 18 times. And you go, man, that's crazy. We rolled the number 7 18 times. Because according to quote unquote probability, if it happens with a probability of 1 out of 6, with 72 throws, we should get it 1/6 of 72, or 12 times. And we got it 18 times. So the question is this a random fluke? Like, did we just happen to get unlucky or really lucky, however you want to look at it, and got 18 outcomes where it was the number 7? Or is something wrong with my dice, right? Like, did I somehow get these weird dice that happen to land on the number 7 more often than it should? Like, should I go to the store and buy some new dice and say, you know what, the dice that came in the box, they're no good. They will land on the number 7 too often, right? So how do we answer this kind of question? Well, we need to learn the rules of probability to help us decide whether this is something that's probable or improbable. And so, as we start talking about probabilities, there's a couple notions of probability that we're going to discuss. And so, really, we're going to focus mostly on theoretic probabilities, but I do have to discuss empirical probabilities, right? And so at its heart, probabilities are numbers that express how likely or unlikely a particular outcome is. So theoretic probabilities are what we call long-run relative frequencies, long-run relative frequencies. So long run means you're going to repeat some random trial a lot of times, some number that approaches infinity, okay? And we can use mathematical rules to figure out these theoretic probabilities, okay? So, one simple example, I think we're all kind of familiar with the notion that when you flip a coin, the probability it lands heads is 0.5, right? Now, how do we get that? Well, we said, there's two sides to the coin. Each side of the coin has an equal chance of landing, and therefore the probability that it lands on one of those sides is going to be 1 out of 2 or 0.5. That is a theoretic probability, okay? All right, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter A. Letter A as in apple. A as in apple. Go ahead and jot that down. That is your first view quiz answer for today. So we just talked about theoretic probabilities, and that's what we're going to focus on for the majority of today's lecture. The other side is empirical probabilities. Empirical probabilities are probability estimates. They're just estimates. They're not based on some kind of theory or math, okay? And they're based on observations from some kind of experiment or real life process. Sometimes you can even get empirical probabilities from a simulation, right? And we need empirical probabilities to estimate probabilities when the math doesn't exist to figure out the theoretic probability, right? So a silly example is, let's say you're from another planet, you've never seen a coin before, right? Or maybe someone says, here, I've got this magic coin, and this is not like any other coin. And you go, well, maybe the probability it lands heads is different, right? And so anyway, you flip it 50 times, and out of 50 times, it lands heads 23 times. So your estimate of the probability that it lands heads is going to be 23 out of 50, or something like 0.46. That's going to be your estimate of the probability based on the trials that you've conducted. Another example, and this is probably a more relevant example, is, in medicine, it's not like we can just look at the properties of a medication, look at the properties of a person, and say, there's some kind of machine that just makes a theoretic probability prediction. That math doesn't exist, right? So we can ask, what's the probability that a certain medical treatment for a particular patient will be successful? So for example, we can say, one of the treatment options we're considering is surgery for, some kind of operation to remove like a tumor or something like that, okay? And when we do that and they say, this surgery has a 70% probability of success or 80% probability of success, where are they getting that number, okay? Well, what they're doing is they are going to be looking at, hopefully, other data that they've collected, and they say, we've done this surgery before. We've done it for other patients, that have kind of similar medical conditions, similar background demographics, meaning like maybe they're the same age and same gender as you or whatever it is. And in those patients, it was successful 80 times out of 100. And therefore, our estimate for your success is going to be 80%, something like that. Now, in some cases, there's not much data, and so your empirical estimate is going to be off. You know, when you hear something like, what is the effectiveness of the Pfizer vaccine? That's an empirical probability estimate. They said, we gave it to this many people, and this many people got infected. When we gave it to all of these people, on the other hand, we gave the placebo to this many people, and the people who had placebo, you know, a certain number got infected. And so those, we're looking at real life numbers, we're kind of comparing those, and we're coming up with an estimate for the effectiveness of the vaccine. It's not like some theoretical math exists where you can say, oh, these are the properties of the vaccine, and therefore we know this is how effective it's going to be. So empirical probabilities are very important, but it's going to be based on data collection. So theoretic probabilities are based on these long run relative frequencies, whereas empirical probabilities are based on relative frequencies, but those relative frequencies come from actual observations. And the two are related in that as you perform more and more real life trials, the observed relative frequency, that is the empirical probability, is going to approach the theoretic probability. And that's known as the law of large numbers. And that's what keeps casinos and insurance companies in business, right? So all of the games at the casino are set up in such a way that according to the rules of probability, the house or the casino has an advantage when you play the game. And anytime somebody actually gambles and plays a game, they might get lucky and win and take money away from the casino. But in the long run, with millions of people playing, millions of games over the course of the year, the casino is going to make a profit. And in fact, the casino wants people to play or wants people to win, because when people win, they feel confident. They feel like, oh, we should do this again. And what they want is people to play a lot because of the law of large numbers. The real life trials are going to approach the theoretic probabilities, which are designed to be in favor of the casino itself. Okay, so today we're going to just spend a lot of time. The rest of today's lecture is all about finding theoretic probabilities, and we're going to look at the rules for finding these theoretic probabilities. So first, we got to cover a little bit of notation. And we're going to say, let's say there's some event, and we're going to call this event the letter A. All right, we're going to denote whatever event it is as with the letter A. And we're going to say the probability of event A is written as the probability of A like this. Sometimes it's written as probability of A like this with a P. P of A or PR of A. Either way is fine. And if A is the event that the coin lands heads, we might write something like this. Probability of A is equal to 0.5. Right? We can also write something like this. Probability of heads is equal to 1/2. And throughout this class, I will use decimals, fractions, percentages interchangeably. So, you know, you might see me write 0.5, 1/2, 50%, things like that. One thing that you have to be careful not to do, because this is not correct, is to say that A equals 0.5. Don't say A equals 0.5. You have to say the probability of A, probability of the event is 0.5. A itself is the event. The event is not 0.5. It's that the probability of the event is 0.5. So you have to say the probability of event A, or the probability of A, is 0.5, okay? Probabilities are always going to be a value between 0 and 1. And so mathematically, or using symbols, we might express this for any event X or any event A. 0 is going to be less than or equal to the probability of X, meaning probability of X always has to be greater than or equal to 0. And the probability of X always has to be greater than or less than or equal to 1. Probabilities can be expressed as fractions, decimals, percentages, and all of those things are interchangeable. So you might see any of those things. If the probability of an event is 0, then that means that thing will never happen, okay? It is impossible, it never happens. Whereas probability equal to 1 means that the event is certain to happen. The event is certain, guaranteed, things like that. So those are your basic probability rules. And so now we have this notion of the complement, okay? The complement is spelled with an E, meaning it is what completes the kind of I guess the picture versus, complement with an I, which is just kind of a nice thing that you say to somebody. So the complement of A is the outcome that A does not happen. And so you can write the complement as AC for A complement, or perhaps you might write not A. And so if we say event A is the outcome that a coin toss lands heads, then the complement of event A is going to be the outcome that the coin toss does not land heads. And that's going to include basically all possible outcomes where the coin doesn't land heads. Perhaps the coin lands tails, maybe the coin rolls away, the coin lands on its side, the coin explodes midair, who knows? Okay. For simplicity, we can say A complement. The A complement means that the coin lands tails, and we're going to just ignore any other thing that happens. So either it lands heads or it lands tails, and if something else happened, like it lands on its side, then we're going to just ignore that, okay? And so as far as calculating the probability of that, if event A has probability, some number denoted by the probability of A, then the complement, that is the probability of A complement, is going to be 1 minus the probability of A. And one more thing, and then we'll do an example. In some cases, we have what we call equally likely outcomes. So in some simple cases, we have equally likely outcomes where, I don't know, it could be something like drawing a card out of a deck. Every single card has an equal chance of being selected. And event A, whatever event we're talking about, could be made up of several of these equally likely outcomes. This only applies if all of the outcomes are equally likely, which is not always going to be the case. And when we do this, the probability can be found by doing this. We're going to say the number of outcomes in A divided by the number of all possible outcomes will be the probability of event A, or event A is some conglomerate of multiple possible equally likely outcomes. All right, so let's take a look at an example. All right, so imagine you've got some kind of cup of M&M candies. I don't actually have a cup of M&M candies. I've got a thing of paper clips, but just imagine I've put like candies in here, okay? Here's a little picture. And I don't know, you decided to do this and you decided to count out the total number of candies. There's 168 pieces of candy. 30 of those pieces are brown, 25 are red, 28 are orange, et cetera, et cetera. You count out all of the different pieces of candy and their colors. And you take this cup of candies and you shake it up, and you're gonna, you close your eyes and you're gonna draw one out at random, right? And drawing a paper clip, okay? But pretend this is an M&M. And so the question is, what is the probability that we end up selecting a brown piece of M&M candy? Okay, well, we're going to say every single one of those candies has an equal chance of being selected. That's all 168 have an equal chance of being selected. And out of those, 30 of them are brown, and therefore the probability of drawing a brown piece of candy is going to be 30 divided by 168. We get some probability, something around 0.1786. So something a little under 18%. All right, I think that's pretty simple. Question for this class, should we give answers with 4 decimal places unless otherwise specified? I think 4 decimal places is a good number. I think on Sunday's quiz, I asked for something like 3 or 4 decimal places for most of your answers. And if the quiz question, just so you know, if you keep more decimal places, you will not get deducted. So if the question says like keep 3 decimal places and you provide 4, you will not lose points, right? So if the answer is like 0.124 and you decide to enter 0.12397, you won't lose points, okay? So unless I mess up my quiz, and then I would fix it, right? If I make a mistake, then I'll fix it. But you won't lose points for providing more decimal places than what it asks. There's a possibility that if you don't provide enough decimal places, you could end up getting it wrong. Let's look at the complement, right? So what if somebody says, what's the probability that I don't get a brown piece of candy? Okay, what is the probability of not getting a brown piece of candy? Okay, well, the probability of getting a brown piece of candy was 30 over 168, or something a little under 18%. So the probability of that not happening is going to be 1 minus the probability of getting a brown piece of candy. So 1 minus 30 over 168, or something a little over 82%, 0.8214. Okay. So far, so good? All right, great. Oh, thank you for that thumbs up. Okay, let's take a look at this two-way table here. And we are going to combine events with and. So we might say some event is A and B, right? An event belongs to A and B. When we say that, then both of those things have to be true. So here is a table. We're going to pretend I just completely made up some numbers. We're going to say we have 208 people. This is, I guess, for some classroom, a big class, 208 students. And we did a survey and we said, are you in your first year? Are you in your second year? Are you in your third year? Or are you on your fourth year or higher? And then we asked, are you from California or are you not from California? And let's say these are the numbers here, right? We have a total of 208 people. And what we're going to do is we're going to select one person at random. So all 208 people have an equal probability of being selected. And the question is, what is the probability that the person we select is from California and is a first-year student? Okay. Well, in our table, we have 40 people that fit that criteria. We have 40 people that are both from California and is in their first year. And so our answer is going to be 40 divided by 208, around 19%, a little over 19% there, 0.1923. We can ask the word or, okay? Or in statistics is always going to be an inclusive or, which means event A. So if we say A or B, we mean A or B or both, okay? That's an inclusive or versus, say, the exclusive or. I think most languages with the or word, the or is ambiguous in that, just as a side note on the ambiguity of the word or, I could ask you the question, do you like chocolate or vanilla ice cream? And you would answer that with yes or no, in that you're happy with chocolate or vanilla ice cream. So that's you like chocolate or vanilla or both, okay? I could ask the exact same question. Do you like chocolate or vanilla ice cream? And in that case, you would say, oh, I prefer chocolate, or I prefer vanilla, or something like that. And it's the same words, just a little bit of weird pausing to kind of differentiate between whether we're using an inclusive or an exclusive or, but when you write it down, do you like chocolate or vanilla ice cream? It's not always clear if that's going to be an inclusive or an exclusive or. But anyway, in statistics, it's always going to be an inclusive or. And so when we say, what is the probability that a person is from California or is a first-year student? Here, we want to include all people from California. We want to also include all first-year students and the people who are both from California and first-year students. So if we do this, we can look at all people from California. We've got 40 first years, 55 second years, 20 third years, 5 fourth years or higher. Plus we have first year students who are not from California, plus 30. And we can add all of these boxes up, all of these numbers up, and we get 150 students who are from California or first year students or both out of 208, something around 72%. One way we can look at this is with this Venn diagram. When we talk about the probability of A or B, what we're mean to say is just kind of this total area that's colored in, the blue, the green, and the yellow all together. And we can calculate this using this, I don't know if shortcut is the right word, this formula. We can say the probability of A or B is going to be equal to the probability of A, which is this entire circle, both the blue and green parts, plus the probability of B, which is this entire circle, both the yellow and green parts, okay? But if we add these two directly, if I just do probability of A plus the probability of B, I have kind of double counted the green. I've counted the green twice, and I only want to count it once. So what I'm going to do is I'm basically going to subtract off this green part, and basically I'm going to have the blue and green right here. And then if we imagine taking this minus this, then we're going to just be left with the yellow crescent moon. And that will give us the total area of the blue, green, and yellow without double counting the green. So if we do this, we will end up getting this, right? So, oh, the question back here, yes, why did we do 30 here? This is, yes, indeed, the answer is provided in the chat. It is the first years who aren't from California, because we want everybody from California and everyone who's a first year. And so we've got everyone from California who also is not a first year. We also have everyone who's a first year that's not from California. So we're adding all of those people. Okay, so trying this back, we can answer the exact same question. We're going to get the exact same answer, but our approach is going to be slightly different. And so if we say, what is the probability that someone is from California or is a first year? We can do the probability from California, and we can just look at this total, 120. We can do the probability of being a first year, which is going to be 70 out of 208. And we're going to subtract off the overlap, because this 70 is made up of the number 40 plus 30. And this number 120 is made up of all four numbers in this row. And so probability coming from California is going to be 120 over 208. Probability of being a first year is going to be 70 out of 208. And then we want to subtract off this overlap because we don't want to double count it. So 120 plus 70 minus 40 is going to give me 150. And this indeed gives me the exact same number as I did if I counted up all the individual boxes. Okay, so we got 150 that way. 150 out of 208, we get 150 out of 208 this way as well. That's okay with everyone? Sometimes we get events that are mutually exclusive. Two events are mutually exclusive if the two events cannot happen together. So if events A and B are mutually exclusive, then we would say the probability of A and B is equal to 0. Meaning if A happens, then B can't happen, or if B happens, then A can't happen. And so if that's the case, when we talk about the probability of A or B, this is kind of our formula that we start off with, we can simplify this to just the probability of A or B is going to be the probability of A plus the probability of B, okay? And that's because this part, the probability of A and B, is going to be 0, and so we can just kind of ignore it. So if we know two things have no overlap, there's no possibility that they're both going to happen together, and we say, what's the probability of this thing or this thing happening? You know, we don't have to worry about the and. So we just add those individual things. So for example, you cannot both be a first year and a second year. You know, maybe you're a first year with second year standing, and you might go around bragging about that or something, but you know, you can't, this cannot be your first year and your second year at the same time. So if we talk about, what's the probability that a person is a first-year student or a second-year student, all we have to do is we can just say, okay, how many first years do we have? 70. How many second years do we have? 95. The total of those two things is going to be 165. And that's going to be our answer, 165 over 208. We don't have to worry about subtracting off the overlap. Anytime you do the or, you have to subtract off an overlap. But here, there's no overlap. There's no overlap to worry about. So we just take the probability of first year, 70 over 208, plus the probability of being a second year, 95 over 208. We add those together, we get 165 over 208, something around 80%, 79.7933. The labels of the events, whether we call it A or B, and the order that we put them in it doesn't matter. So the probability of A and B is exactly the same as the probability of B and A. The probability of A or B is also exactly the same as the probability of B or A. So don't worry about that. All right, we're going to keep going here. And now we're going to complicate things with conditional probabilities. So this is a little bit of new notation here. We've got probability of A, and this vertical bar here means given. So this would be read as the probability of A given B. So it's the probability that event A happens given the fact that event B happens. So an example here, and I'm just playing off of maybe some stereotypes of the state California and the state Texas. And so we're going to say, what is the probability that someone drives a truck, like someone drives a pickup truck, if that person is from California, versus what's the probability that someone drives a pickup truck if that person is from Texas? All right. And so just kind of I think a lot of Texans are kind of proud of this image that they present, that a lot of people in Texas drive these big trucks and things like that, and they're very proud of their trucks. Whereas in California, a lot of people do drive trucks, but in California, we're also like all about our Priuses and Teslas and things like that, right? So, anyway, the probability of drives truck given from California is going to be the probability that someone drives a truck if we're given the fact that the person is from California, versus the probability that the person drives a truck given that they are from Texas, okay? Does that kind of make sense there? And so the way we would go about calculating this probability, the probability of A given B, whatever these things are, is going to be found by doing the probability of A and B, and then we would divide by the probability of B, right? If you have some kind of table, you can also just use the count of A and B divided by the count of B. But this is also important. You are not allowed to just swap events around. The probability of A given B is not going to necessarily be equal to the probability of B given A. And in fact, they're not going to be equal in, most cases. So you cannot do this. These two things are very different. The probability of A given B is not the same as the probability of B given A. All right, so here is just some completely made up data. Don't use this and turn this into some kind of like this is fact or anything. This is just completely made up data. So we're going to just pretend we took 2,745 people. Some of these people came from California. 1,575 people came from California. 1,170 came from Texas. And of those, some people drive trucks. Some people do not drive trucks. And so we're going to ask this question. What is the probability? So we're going to pick a random person from this table. All 2,745 people have an equal chance of being selected. And we want to know, what is the probability that this randomly selected person drives a truck given that they are from Texas? What's the probability that a randomly selected person from this table drives a truck given that they are from Texas? Okay. The way we would write this notationally is probability of truck, vertical bar, given Texas. The probability of truck given Texas. So this basically says we're going to limit ourselves to just people from Texas. It's going to be the probability of truck and Texas divided by the probability of Texas. So in the numerator, we're going to put the and number, which is going to be the count of 420. And in the denominator, we're going to put in the probability of Texas, which is going to be 1170. So if we know somebody is from Texas, we can limit ourselves to just these 1170 people. Of those, 420 of them drive a truck. So the probability that someone drives a truck, given that they are from Texas, is just under 36%. Okay. Here is a similar question phrased just a little bit differently. What is the probability that a randomly selected person from California drives a truck? So now we're going to randomly select a person from California. We're basically limiting ourselves to just the 1,575 people. Maybe I'm getting ahead of myself. Well, notationally, this is written like this: probability of truck, given that the person is from California. We're limiting ourselves to just these 1,575 people. That's going to be the number that goes in our denominator. The number that goes in the numerator is going to be 470. That's how many people from California actually do drive a truck. So that's California and truck. That's going to be the numerator. 470 divided by 1,575. And so that number is just under 30%, 0.2984. I hope those are good with everybody. And lastly, here's another question. Similar sounding, but also different. What is the probability that a randomly selected person is from Texas if we know that they drive a truck? So this time, the part that is given to us, the piece of information given to us, is the fact that this person drives a truck, and we have a total of 890 people. So, and now the question is, what is the probability that the person is from Texas, given that we know they drive a truck? So out of the 890 people who drive trucks in our data set, 420 of those came from Texas. And so our number is around 47%, 0.4719. And I kind of want to just pause here, make sure everybody's okay with these questions, what's been presented. And, you know, I want you guys to be okay with just like the subtle differences in wording, and that we can go from the wording to the notation and then figuring out the numbers. Okay, some of you guys gave me thumbs up. Maybe only 2 of you out of the 79. So thank you, another 2 here. But I hope, and of those, all right, thank you guys. And those of you who have your cameras on, you know, some of you are nodding your heads. So that makes me feel good. Okay. All right. And someone's giving me laughing tears. I guess that's a good sign. All right, just a couple more examples here. These are not conditional probabilities, but if we said, what is the probability that someone drives a truck and is from Texas? Well, here we're selecting a person at random. 2745 is going to go in the denominator. 420 goes in the numerator. So our answer is going to be 0.1530. What's the probability that a randomly selected person drives a truck or is from Texas? So in that case, we're going to do the probability that someone drives a truck plus the probability that someone is from Texas, and we're going to subtract off the overlap. So we're going to do 890 over 2745 plus 1170 over 2745 minus the overlap 420. We get 59.74%, just under 60%. And here's one where we have 2 mutually exclusive events. What's the probability that a randomly selected person is from Texas or from California? And the way we have this, we're going to say, you know, your current residence has to be one or the other. There's no overlap. And so we would just kind of do this and add this, and there's no overlap to subtract. And if you add those up, you're going to get 1. Right? These 2 numbers add up to 2745. 2745 over 2745 is 1. Okay. Hope that's good. Let me go ahead and give you your second view quiz answer for today. Today's second view quiz answer is the letter B. Letter B as in bear. Letter B as in bear. That's your second view quiz answer. We can do a little bit of algebraic manipulation, and we can say the probability of A given B, this is kind of our definition that we've been using, is the probability of A and B divided by the probability of B. And if I multiply both sides by the probability of B, assuming that probability of B is not 0, we're going to multiply both sides by that, and we would get the probability of B given, or multiplied, sorry, probability of B times the probability of A given B is equal to the probability of A and B. We can also kind of swap all of our letters around, and this is also going to be true. The probability of A times the probability of B given A is going to be equal to the probability of A and B. And if we kind of rearrange some values here, we can figure out and get the probability of A and B equal to this thing, the numerator, probability of A times the probability of B given A divided by the probability of B. That was a lot of A's and B's that I just kind of rattled off here. I think we'll do an example, and hopefully that will make a little bit more sense of what I'm trying to show you guys with Bayes' rule. So in this example, we're going to go to the airport, and we're going to say, if there's a storm, the probability that the flight gets delayed is going to be 0.6. So this is a conditional probability. The probability that there's a delay is going to depend on whether there's a storm or not. It's conditional on whether there's a storm or not. So if there is a storm, we have a 60% chance of a delay. And if there's no storm, the flight can still be delayed, but the probability of delay is much lower, something around 7%. And we're going to say the weather forecast says that the probability of having a storm is 25%. All right, and so our first question is going to be, what's the probability that there is a storm and the flight also gets delayed? The probability of a storm and the flight gets delayed. Well, we can use kind of these rules right here. The probability, if we call, A the delay and B the storm, we can say, what's the probability that we get a storm and a delay? This is going to be found by taking the probability of a storm multiplied by the probability of delay given storm. So here we're just going to call basically storm is event B and delay is event A. And I'm just kind of plugging that in to get this. And we're going to say 0.25 is the probability of a storm. And we're going to multiply that by the probability of a delay given a storm, which is 0.6. And so first there has to be a storm. And on top of that, there's a 60% chance if there is a storm that it gets delayed. And when you multiply those two things together, we get about a 15% chance that these two events are going to happen. Let's complicate things a little bit more, and let me try this example out. So we're going to ask, what is the probability that just the flight gets delayed? The flight gets delayed, all right? And then we'll also ask this question later, but let me do a little slide here, hand-drawn thing. And so we're going to say what we have the probability of a storm is 0.25. So here I'm going to just, we'll go back a couple slides and we'll just use this as a reference, right? So we got the probability of storm is 0.25. The probability of delay given storm is 0.6. Probability of delay given no storm. So probability of delay given storm, 0.6. The probability of delay given no storm, 0.07. Is this, am I writing large enough for you guys to be able to see on your screen? This is okay? All right, great. So what we want to do is I'm going to draw what is known as a probability tree, okay? And we're going to say that in a life, there are two possibilities. There are storms, times where there are storms, and there are also times where there are no storms, okay? This is not some metaphor for something greater, but I guess it could be. But and at the airport, if there is a storm, then we could end up having a delay, or we could have no delay. We can have a delay. Even if there's no storm, you can still end up with a delay, or you can have no delay. And what we're going to do is we're going to put down the probabilities on each of these branches. So what is the probability that we end up having a storm? Well, that's going to be 0.25. This is going to be the probability of the storm goes on the branch. We put 0.25. So what number goes on this branch over here? The probability that there's no storm. What number should I put on this branch? Yeah, I see it in the chat. 0.75, right? Because there's only two possibilities. There's either a storm or there's not. These things are complements of each other. So these two things have to add up to 1. So if I've got 0.25 here, I've got to have 0.75 here. Okay, let's see. What number should I put down on this branch? This says there is a storm. This is what has happened. This has been given to us, and we want to know if there is a storm, what's the probability of the delay? So the number that goes on this branch is this number, the probability that there is a delay given that there's a storm. And so if there's a 60% chance of a delay, then what's the probability of having no delay over here? Yeah, exactly. I see that in the chat, 0.4. That's going to be the probability of, and the way I would write this is going to be no delay given storm. Okay, all right, so let's just finish this out. Down here, even if there's no storm, we can still end up with a delay. That's going to happen 7% of the time. This is going to be the probability of delay given no storm. And down here, then I'm going to do the complement, which is going to be 0.93, and that's going to be the probability of no delay given no storm. Okay, and what we'll do is we'll go down the branches and we will multiply 0.25 times 0.6 gives me 0.15, and this is the probability of storm and delay. .25 times 0.4 gives me 0.1, and this is going to be the probability of storm and no delay. .75 times 0.07. So I see in the chat, and you guys are answering each other correctly. Yeah, anytime you have kind of this little node with branches coming off, all of the probabilities on the branches have to add up to 1. That is correct. All right, well, 0.75 times 0.07, I'm actually not that good. Well, let's see. Let's pull up our calculator. Oh my goodness, this is way too big. How do I shrink this? Calculator, okay. 0.75 times 0.07, 0.0525. And this will be probability of, I'm going to just write no storm and no delay. And here, 0.75 times 0.93. 0.75 times 0.93. 0.6975. Oh, that was a delay. Sorry, thank you. Thank you for catching that. Probability of no storm and a delay, and this one is 0.6975. And this one is probability of no storm and no delay. All right, great. Okay, so let's not lose track of what our question was. Our question was, what is the probability of the flight's delayed? Okay, so we look at our branches and we say, all right, where do we end up with a delay? Okay, we end up with a delay here. This is a delay. And we end up with a delay here. Okay, so what we're going to do is we're going to add this number, 0.15 and 0.0525. And we're going to write something. Maybe I'll use a different color here. I'm going to say the probability of delay, well, we'll add these two numbers, is going to be 0.15 plus 0.0525. And we'll get 0.2025. 0.0525. Do we feel okay about the calculations to get here? All right. All right, and I think I put this all in this kind of picture here. So this is in the notes. I think I have it all written out there. Okay, great. And here is also, if some people prefer, I think most people prefer drawing the tree, but some people actually prefer having the formulas all written out. And so if you like just the formulas written out, you can also do it this way, and you'll get the exact same answer because the numbers are all being multiplied the same, 0.15 and 0.0525, and you get 0.2025. All right, the next question says, we go to the airport to pick up your friend and you end up seeing that the flight was delayed. And the question now is, what is the probability that there was a storm? So this is like, I don't know, you have to imagine the time before you had cell phones, where now, like when you pick up your friend, you can track the actual flight and see what's happening in the air, and you know the exact moment that they land and things like that. But there was a time where you would just kind of show up at the airport to pick up someone, and you'd kind of look up on the screen and they'd say delayed, you know, inbound from, who knows, Chicago, delayed. So anyway, we're going to just say, oh, you know what, there's been a delay. And we go, I wonder if there was a storm. It's a contrived scenario, but just go along with it, please. All right, so what we want to do is we want to say, okay, you know what, we find out as we're kind of looking up at the screen, there's a delay. I mean, we know that there is a delay. So this kind of eliminates from the realm of possibility, this is not going to happen, and this is not going to happen, right? So now our world is only limited to kind of this, right? So this is the outcome where we had no delay. This is not it, right? So these are our two possible outcomes. Okay. And the question now is, well, if this is it, what's the probability I end up, oh, what did I do? Something, uh-oh. Oh no. Oh, geez. I did something on my thing and I don't know how to fix it. Okay, well, all right. It's better than nothing. All right, so so we want to know, okay, well, what's the probability I ended up going down the storm route, right? So how did I end up here, right? And how did I end up in this scenario where I'm delayed? Well, maybe I went down this route. Maybe I went up down the no storm route and I ended up with a delay. Maybe I went down the storm route and I ended up with a delay, right? So this is kind of like pick your adventure. How do we end up here with a delay? Well, out of the total possibilities of a delay, 0.15 was storm and delay, and 0.0525 was no storm and delay. So our answer, and I hope this makes sense here, is, so we're asking what's the probability that there was a storm given that there was a delay? Okay, well, in the denominator, we're limiting ourselves to just the outcomes where there's a delay. And from our previous slide, we know that this number, we're limiting ourselves just to these kind of outcomes. Those two outcomes add up to 0.2025. And of those, we want to know, well, what's the probability that, you know, I had gone down the storm route, right? So this is going to be storm and delay. And that calculation was 0.15. So our answer is going to be 0.15 over that, 0.15 divided by 0.2025. And I get 0.74074, so 0.7407. And that's going to be our answer here. So here is the slide. I guess I rounded to 0.741. That's also fine. And that's going to be if we know there's a delay. That's the part that's given to us of those. 0.15 was the storm. And so we do 0.15 over 0.2025 and we get 0.74. Okay. Is that all right? So, all right, and there's your solution. Okay, any questions before I move on to independent events? Okay, all right. If two events are independent, then the outcome of, what that means is that the outcome of one event is not associated with the outcome of the other event, right? So another way to kind of phrase this, as far as, in terms of the rules of probability, is that if you have two events A and B, then the probability of A happening, given that B has happened, is the same as the probability of A happening, given that B did not happen. So whether A happens or not does not depend on whether B happens or not. So the probability of A given B is equal to the probability of A given not B, and that's just the probability of A, right? So the probability of A happening is not affected by the probability of B. Whether B has happened or doesn't happen doesn't matter. It's just the probability of A, okay? Whereas, when we're kind of looking at the example with the people driving trucks, whether they were from Texas or not, we would say, if we know someone's from Texas, we might say, oh, they're a little bit more likely to be driving a truck than if we know the person's from California or something like that, right? So that's kind of the idea here. So the reverse is also true. If A is independent of B, then B is independent of A. And if A is not independent of B, then B is not independent of A, right? Or if we say B is dependent on A, then A is dependent on B. If they're not independent, then neither of them are independent. If they're independent, then both of them are independent of each other. Okay, so let's look at our California and Texas truck example. And let's actually look at the numbers and let's answer this question. Is driving a truck independent of being from Texas? So, our stereotype answer is that, if we know someone's from Texas, they're a little bit more likely to drive a truck than if we knew the person was from California, right? And I mean, we can turn this from, driving trucks to, any other thing that we want, but I think this is like a mostly harmless stereotype here. So first we're going to ask, what is the probability that someone drives a truck given that they are from Texas? So if the person is from Texas, given that they're from Texas, we're going to put 1170 in the denominator. And how many people drive trucks? 420 out of 1170. And therefore the probability that someone drives a truck given that they're from Texas, and again, this is completely made up numbers and made up data, our number is 0.359 or something around 36%. If we say, what's the probability that someone drives a truck if they're not from Texas, okay? And in our case, not from Texas means they're from California. Well, we have 1,575 people not from Texas, and of those 470 drive a truck. So the probability of driving a truck, given that they are not from Texas, is a little under 30%, 0.2984. And so these two numbers are not equal. And that means the people from California and people from Texas have different probabilities of driving a truck. And we would come to the conclusion that driving a truck is not independent of being from Texas. Is that reasoning and logic okay with everybody?
I'm kind of confused a little bit on the last, how it said driving a truck is not independent of being from Texas. Can you explain that a little bit?
So again, independent has so many meanings, and specifically when we're talking about probabilities, it just means the probabilities of these two events, we would adjust our numbers. So if somebody says, what kind of car do you think this person drives, right? And if they say, oh, the person's from Texas, you might say, oh, they're a little bit more likely to drive a truck. Is that a statement that feels okay, at least based on these numbers here? So if we say, if we know the person's from Texas, the probability that they drive a truck is something around 36%. Whereas if we know the person is not from Texas, the probability that they drive a truck is a little bit lower at, let's say 30%. Okay, so we've got 36% here versus 30% here. And so the fact that the probability should be adjusted whether or not the person is from Texas or from somewhere else or from California indicates to us that those two things, driving a truck and being from Texas, there's some kind of association. Okay, and we're not making a cause and effect relationship. We're not saying that one thing that just by being in Texas somehow that makes you want to drive a truck. Who knows, right? But all we're saying is just that if we're looking at these numbers, the people from Texas, there's a higher proportion that drive trucks than people from California. And so those two things, those quote events, are not independent. Okay, and so I don't want you to think of independent meaning like this thing is causing this or is not causing this or somehow caused by the other. All it just means is that, if we're looking at these proportions, the proportions are different. Whether, the proportion that drives trucks is different in Texas than it is California, at least according to this fictional table of data that I've made up. Is that okay?
Yes, thank you.
Okay. So here's just another example. And again, I've completely made up these numbers, but I've picked out these numbers in such a way that it would fit the example here. So we're going to ask, is being left-handed independent of wearing glasses? Okay, so we've got people who are, and we're just going to, just for simplicity, and I know this is not always the case, but we're going to just say we have people who are right-hand dominant and people who are left-hand dominant, and we have people who wear glasses and people who don't wear glasses. And the question is, when you say glasses, do you mean corrective lenses or what? It doesn't matter. We're just going to kind of simplify this and just say glasses versus no glasses, left-handed versus right-handed, just for the sake of this illustration here. And so what we want to know is if these two things are independent, and if they're independent, then we could check to see if these two probabilities or proportions are equal to each other. If they are independent, then what we should see is that the proportion of people who are left-handed is the same whether the person wears glasses or whether they don't wear glasses. So if someone wears glasses or doesn't wear glasses, that shouldn't affect the proportion or probability that someone is left-hand dominant. So we're going to do these checks. We're going to say, okay, well, what's the probability that someone is left-handed if we know that the person wears glasses? So we have 60 people who wear glasses. Of those, 6 people are left-handed. So we do 6 divided by 60, and we get 10% of glasses wearers are left-handed. And then we go to the other side and we say, okay, well, how many people don't wear glasses? That's going to be 140 in our denominator. And of those, how many people are left-handed? We have 14. And therefore, the proportion of people who are left-handed among non-glasses wearers is also 10%. So the probability that somebody is left-handed is 10% whether or not the person wears glasses or doesn't wear glasses. Okay, so if somebody says, what's the probability that someone is left-handed? You'd say 10%, and go, hold on. I got to give you some more information before you make that conclusion. Okay, yeah, what information are you going to give me? Guess what? This person wears glasses. And you'd say, how is that relevant? How is that going to help me figure out whether the person is left-handed or not? That it doesn't help you. And that's because being left-handed is not dependent or is not in any kind of way associated with wearing glasses. Okay. So we have 0.1, 0.1. Those two probabilities are equal, and therefore people who wear glasses and people who don't wear glasses have the same probability or same proportion of being left-handed. And we would come to the conclusion that wearing glasses and being left-handed are independent. Those two events are independent. So if event A and B are independent, then these two things, then this equation is going to be true. Probability of A given B is equal to probability of A given not B. And we can swap the letters B and A, and this will also be true, right? So the probability of B given A is also going to be equal to the probability of B given not A, right? So what we checked on the previous slide was we said, what proportion of glasses wearers are left-handed and what proportion of non-glasses wearers are left-handed. We checked that, and those ended up being equal. We could have also checked a similar but different proportion. We could say of left-handed people, how many people wear what proportion wear glasses? And of non-left-handed people or right-handed people, what proportion wear glasses? And we would come, 6 out of 20 would have been 30%, and 54 out of 180, I think, is also 30%. 6 divided by 20, 30%, 54 divided by 180, 30%. We would have gotten the same number, and we would come to the same conclusion, 30%, 30%, they're equal, okay? So you don't have to necessarily do this check. You could have also checked it this way, and you would have gotten the same answer that they are independent. You would have gotten 30% is equal to 30%. Those two are equal, they are independent. What you don't want to do is you don't want to mix it up and say, is the probability of A given B, is that equal to the probability of not A given B, or something like that. So, if you checked this, probability of left-handed wearers given glasses, is that equal to the probability of right-handed given glasses? Those two numbers aren't going to be equal, and this is not a useful comparison to make as far as whether events are independent or not. So here's a question. Let's say there are two events, A and B, and those events are mutually exclusive. And we're going to say both of those events have non-zero probabilities. Okay, so A and B are mutually exclusive, and individually they have non-zero probabilities. So the question here is, if that's the case, could events A and B be independent? Could they be independent? So I want you to think about this for a moment, right? If two events are mutually exclusive, could those events also be independent? Okay, and we'll use our reactions. I guess I'll count to 3 at some point, and you'll give me either the thumbs up, the clapping, or the party hat reaction, or I don't know, the ta-da reaction, I guess is what it is. Thumbs up, clapping, or ta-da, for what you think. Yes, the events are certainly independent, or no, they are not independent, or maybe they could be, or they might not be, right? What we know is that events A and B are mutually exclusive. The question is, are they independent? Okay, so go ahead. I'm going to count to 1. On 3, we'll reveal our answers. Okay, ready? 1, 2, 3. All right, choose your things. All right, so we got 21 party hats, 13 claps, 29 party hats, 15 claps, and 9 thumbs up. Okay, kind of split, with party hat being the most popular choice. The answer is clapping. Okay, the answer is they are certainly not going to be independent. All right, so let's think about this for a moment. Both events have non-zero probabilities, and they are mutually exclusive. All right, so if we think about what mutually exclusive means, it means that A and B cannot happen together. The probability of A and B together is 0, right? So the probability of A and B together is 0, but we know individually they have non-zero probabilities, right? So what that also means, mutually exclusive, is if B happens, then A is impossible, or if A happens, then B is impossible, right? So if we know the student is a first year, we know the probability that they are also a second year is 0. Or if we know the person is a second year student, the probability that they are also a first year student is 0, okay? Whereas independent means that the outcome of one event is not influenced by the outcome of the other. That knowing one thing is not going to help you, is not going to change the probability of the other event. Okay, so that's not what's happening. Once with mutually exclusive events, once you know one thing has happened, then you know that the other thing has a probability of 0. Okay, So if A and B are mutually exclusive, then the outcome of B influences the outcome of A by making it impossible. And so A and B, if they're mutually exclusive, cannot be independent. Right? I hope that makes sense there. Okay, let's we'll keep covering some more of these rules here. And we're going to say that if we have independent events, we can look at the probability of some sequence of events, okay? So we can say if events A and B are independent, the probability of A and B is just the product of those two things, probability of A times the probability of B. And then if you have a whole bunch of events, probability of A and B and C and D, and all of those events are all independent of each other, then the probability of A and B and C and D is going to be the product of each of those probabilities. That is the probability of A times the probability of B times the probability of C times the probability of D. And this will just extend to, you know, however many independent events need to be done. So let's do a simple example here. All right, so let's say you have some special coin, and I don't know if such a coin exists, but we're going to say the probability that it lands heads is going to be 70%, and the probability that it lands tails is going to be 30%. And what we're going to do is we're going to flip the coin 2 times. And coin flips are independent of each other, meaning whether the first coin flip landed heads or tails has no influence on whether the next coin flip is going to land heads or tails. And so the question is, what is the probability that the coin lands heads both times? Okay, where each time we flip it, there's a 70% chance that it lands heads. And if we flip it twice, what's the probability that it lands heads both of those times? Okay, so here we're just going to take the product of those things. So probability of getting heads both times is this outcome. We get heads on the first flip and heads on the second flip. And that means we're going to just multiply these two things together. The probability of heads on the first flip is 0.7. We're going to multiply that by the probability of getting heads on the second flip, 0.7 times 0.7, and we get 0.49. So just under 50% chance, 49% probability of getting heads both times if you flip the coin twice, and each time there's a 70% probability of heads. Right? I think that makes sense. I think most students are comfortable with this. All right, let's say we can just kind of complicate our thing, and we can say we're going to flip the coin 2 times. Coin flips are independent of each other, and we can ask, what is the probability that the outcome of the second flip matches the outcome of the first flip? All right, so outcome of the second flip matches the outcome of the first flip. So what are we talking about here, right? So we can kind of list off all of the possible outcomes as far as 2 flips go. And there are 4 possible outcomes. We can get heads followed by heads, heads followed by tails, tails followed by heads, and tails followed by tails. And so the second coin flip matching the first out flip will be heads, heads, and tails, tails, okay? The second coin flip being tails matched the first outcome of tails. So we're gonna look at the probability of heads, heads, and tails, tails. And we wanna know what's the probability of these 2 things. So we're gonna say, what's the probability of getting heads, heads, or tails, tails? Second flip matches the first flip. These 2 things are mutually exclusive. If the coin landed heads, heads, then it cannot have also at the same time had landed tails, tails. So these are mutually exclusive outcomes. So we can just add those 2 together. We don't have any overlap to subtract off. So we're gonna do the probability of heads, heads, plus the probability of tails, tails. And the probability of heads, heads is found by doing 0.7 times 0.7. And the probability of tails, tails, well, the probability of being tails is 0.3, is going to be 0.3 times 0.3. So this multiplies to 0.49. This side over here multiplies to 0.09, and we get 0.58. Is that good with everybody? Okay, great. Thank you for your head nods. I appreciate that. All right, and then one more here. We'll say we're going to flip the coin 4 times, and all of these coin flips are independent of each other. And we're going to just ask, what's the probability that we get heads all 4 times? So we want to get heads, then heads, then heads, then heads. Okay, well, we're going to multiply probability of heads times probability of heads times, okay. And so we're just going to take 0.7, raise it to the 4th power. We get 0.2401. And that's it. All right, as far as that example goes. Okay, let's cover random variables here, random variables. And let me go ahead and give you your 3rd view quiz answer. Please still stick around for the last bit of class, even though like now that you have all of your view quiz answers, you're like, oh, I don't have to, just stick around. The last view quiz answer for today is the letter E, E as in elephant. E as in elephant is your 3rd view quiz answer for today. Okay, E as in elephant. All right, let's talk about random variables. Random variables are the outcome of a random trial, but the outcome has to be a number. Okay, the outcome has to be a number. So for example, we can say, I'm going to pick a person at random from the room. So that's the random trial. But what we're going to record is the person's age, which is a numeric outcome. All right. Or I could say, I'm going to flip a coin 6 times. That's a random thing, a random trial. And we're going to record how many times the coin lands heads. We're recording some kind of numeric outcome. And a lot of times when we're dealing with random variables, we want to know what is the mean or what is the expected value of the random variable. And one way we can think about the mean and the expected value is that we could do many, 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 many random trials, and we can try taking the average of the outcomes of all of these many random trials, right? So if we just did a whole bunch of these things and what is the average or the mean of all of these things, we can do that, and that would be the expected value or the mean of the random variables. So this is the formula as far as calculating the mean. We use this symbol here. So this is the expected value of random variable y. Capital letter Y is the random variable y, meaning this is the outcome of some random trial. And the mean is used is given by this Greek symbol. It looks like a U, but it's the Greek letter for M, and it's pronounced mu. And what we're going to do is we're going to multiply each possible outcome. Little yi is a possible value that the random variable can take on, and we're going to multiply that by the probability that y ends up being that particular value. We're going to multiply those things, and we're going to add them all up. All right, so this is just some formula. I think it'll make a little more sense when we do an actual example here. So here is just some imaginary scenario here. And we're going to say there is a game here. And what did I put in the thing? So you're going to, take a little arrow and you're going to spin it. Okay. And if it lands over here, you get $0. And if it lands here, you get $1. And if it lands here, you get $5. All right, so this is the game of chance. You're going to kind of spin this little arrow, and this is what we have. And we have the probability, we have the outcome, which is the possible outcomes, yi, and we have the probability that the random variable ends up being that particular outcome. Okay, so we can get 0, we can get 1, we can get 5, and the probability of getting 0 is 0.5, the probability of getting 1 is 0.4, and the probability of getting 5 is 0.1. So one thing is that all of these probabilities have to add up to 1. Let me change my pen color here. All right, is that okay? And what we want to know is we want to find the expected value, right? So the expected value of y is going to be the sum of each outcome yi multiplied by its probability. So here we're going to take each value. We're going to do 0 times the probability 0.5 plus the next outcome, which is 1, multiplied by the probability, the getting 1, which is 0.4, and the last outcome 5, and multiply by the probability of getting 5, which is 0.1. And here you get 0 plus 0.4 plus 0.5. We get 0.9. This is our mean. So when you play this game, your expected winnings is 90 cents in the long run. Okay. Of course, you're not actually going to win 90 cents any one particular time. You're going to play the game. Sometimes you win $5. Sometimes you lose it and you get $0. And sometimes you get your dollar back. And that happens 40% of the time. And if you played this game like 1,000,000 times, you would get back around 90 cents on the dollar. Okay, so not a great game. Worse than most games in Vegas, better than most lotteries. So I think scratchers are something around the 70-cent payout. Most games in Vegas, well, I don't know most, but you know, your better games in Vegas have a 90-something% payout. Depends on the slot machine, just depends on the table, things like that. Okay, is that all right? And so this is also the calculation. When you do that, you get that. Let's find the variance. Okay, the variance is going to be this symbol. All right, you're basically going to take the difference from each value, and it's the expected value. So you have to find the mean first. You're going to square that difference, and you square that difference and you multiply it by the probability there. Okay, so don't get the variance mixed up, or the variance of a random variable and the standard deviation of a random variable mixed up with the variance or standard deviation of just a set of numbers. Okay, so here is sigma squared. And what we're going to do is we're going to take each individual value, subtract off the mean. We're going to square that and multiply by the probability of getting that outcome. So here I've got a few outcomes. I've got our first one. Our possible outcome is 0. We're going to subtract off the mean, 0.9. We square that, and we're going to multiply it by the probability of getting 0. We're going to multiply that by 0.5. And we do this for every possible outcome. So I'm going to do that. I'm going to add the next one. The outcome possible outcome is $1. We're going to subtract off the mean, which is 0.9. We're going to square that difference, and we're going to multiply by the probability of getting 1, which is 0.4. And we'll do this for the last one as well. We can get $5. We're going to subtract off the mean 0.9. We're going to square that, and we're going to multiply by the probability of 0.1. Okay, so this gives me 0.9 squared is 0.81 times 0.5. 1 minus 0.9 is 0.1. 0.1 squared is 0.01 times 0.4. 5 minus 0.9 is 4.1. I don't know what that is. 5 minus 0.9, 4.1. 4.1 squared is 16.81 times 0.1. Okay, and so anyway, when you do this, the calculations, okay, so you get 0.405. I guess I can do this. Okay, so half of this is 0.405. This times this is 0.004. And this times this is 1.681. And you add all of those things up, and you're going to get 2.09. 2.09. That's going to be our variance. All right. Is that all right? The calculation of the variance of a random variable. All right. And again, don't mix up, because you're going to be doing this on the quiz that's going to get posted on Sunday. I'm going to ask you, find the standard deviation of some set of numbers. And then I'm also going to ask you, find the standard deviation of a random variable, right? And so this is the variance here, and say, oh no, what did I do? Are you guys still there? Are you still there? Am I still here?
Yeah, we can see and hear you.
Okay, I don't know what just happened. My screen went blank for a second. I don't know if you saw anything. But okay. All right, so if I ask for the standard deviation, you would just take the square root of 2.09. I don't know what that is. Something, right? 2.09, and we hit the square root. Okay, 1.446. All right, that would be the thing. But if I say take the standard deviation of a set of numbers, the whole process for that is completely different, right? So taking the standard deviation for a sample of numbers is very different for the standard deviation of a random variable, and I don't want you guys to mix them up. Okay, I got a couple more slides. So what is all of this about? Okay, here's another pretend game, right? So this one had a mean of 0.9 and a variance of 2.09, and we just went through the calculations there. And here's another game. We could imagine this game, similar thing. You've got a wheel that you're going to spin. Okay, this game, the max prize of the other wheel was $5, right? You could win $5 and that happened 10% of the time. In this game, you could win $800. You can win up to $800, and it's going to happen about 1 in 1,000 times, all right? You can still also get your dollar back. That happens around 10% of the time, and then the rest of the time you're going to get 0. Okay. So this is a similar game, except the wheel looks different and your max prize is $800. All right. If we go through the process of calculating the mean, which is you just take this outcome and you multiply by this probability, and you take the next outcome and you multiply by the next probability, and you take this outcome and you multiply by the next probability, 0 times 0.899 gives me 0, 1 times 0.1 gives me 0.1, and 800 times 0.001 gives me 0.8. When you add everything up, you still get 0.9. Okay, you also get 0.9. So both games, so this game has a mean of 0.9, this game has a mean of 0.9. So both of them have the same kind of expected payoff in the long run. If you were given $1 to play either game, which game would you play? Both of them have the same mean. So if you had like a whole bunch of these dollars to play the game, but this is not your money, somebody just gives you $1 and says, you got to play one of these games, which one would you choose? The psychology has shown us that time and time again, people prefer this game. This game is more exciting. Yeah, so people have said they're going to play the second game. The second game is more exciting. There's a chance to win $800, which is exciting. Whereas the other one, like your grand prize is $5. I mean, that's fine. I'm not going to complain, but $800 is a lot more exciting. And really, this is what state lotteries or just lotteries in general do, is that they say you can win $10 million, $100 million, and they make the grand prize this really, really, really big number with a really, 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 really low probability. And yet people play because the idea of winning a huge number is a lot more exciting, okay? And that's kind of the psychology of lottos and stuff like that. And when you do the calculations for the variance, and I have it all written out here, and I hope that's good enough that just doing kind of one of these examples by hand is sufficient, and you can kind of follow the work. The variance of this thing is much greater, 639.29, okay? It's much higher, the variance versus this variance, 2.09, right? So the variance over here, way bigger. And what that means is just like, if we think about what kind of money you can win from either this game or the other game, is that there's going to be a larger kind of disparity in terms of the different outcomes that could result from this game of higher variance. And truly the most boring game would be if you spin the wheel and there's a 100% probability that your outcome is 90 cents, okay? Nobody would play that game, right? Because that's not even a game. That's just giving you $1 and then you get 90 cents back or something. That's just a tax. That's not a game that people would want to play, okay? And so, you know, there's yeah. So anyway, high variance just kind of means there's a greater kind of difference in the terms of the outcomes here, and we can kind of measure it directly as far as the random variable goes. Okay, and so, so I've written a little bit about that. Both of them have the same mean, but they have very different variances. All right, we will end here for today. Have a good weekend, everyone, and we will see you guys on Tuesday. So have a good weekend, and we'll see you guys then. Remember to turn in your homework and take the quiz on Sunday. It's due, I guess, Monday, 11:59. So we'll see you guys then.
Thank you.
Thank you.
Thank you.